So the JOSM data, as you recall, that is just an acronym, stands for Joint OSNs Monitoring Data. And we use this amongst ourselves, and that's how I named the data. It is really a list. It surveys, species, and counts. So the easiest of the tables is the species element, which is just going to give us the English and scientific names for the abbreviated versions. So if you're unsure what oven stands for, probably that's the easiest to guess. But the rest, you can just take this table and look it up. Then in the surveys part of this, you can see site ID, lat, long, date, those sorts of things, which are going to be important when we look at how these different survey events or sites relate to each other. So this is all, if you go and do a survey, you take all these metadata, where that was, when the survey happened, and then maybe once you go back home, you do some GIS. So at the end, this is what you get from GIS, and I'm going to explain it a bit more later. What is the amount of agriculture around that survey point? Urban industrial features, linear features, roads, deciduous, wetlands, coniferous lowland wet environments. So those are summarized based on GIS and kind of joined in this table that is going to give us information about these surveys. And where we have the bird observations, that is the counts table. And I again show you the structure of this. We have a site ID, where that was. Then we have all kinds of other columns with time interval, 1, 5, 1, direction, distance. So these are going to tell us, and there are a bit more human readable versions coded as dur, as duration, dis as distance. You can see 3 levels, 0 to 3, 3 to 5. So those are the sub intervals. These were collected under 10-minute unlimited distance point count protocol. And within the 10-minute, there were sub intervals, 0 to 3, 3 to 5, 5 to 10. So these are the labels you can see here. And in terms of distance, there were 0 to 50, 50 to 100, and 100 plus. So these are coded like this. Then you get the species ID. And this is how we can then turn this into a matrix where we have the survey IDs as rows, species as columns, or maybe the distance or time intervals as columns. So this is the table we are going to use. So now how do we do a crosstab based on this? Let's look at what kind of behaviors we get. In this column, in the count table called detect type 1, and if you want to also see if there is any NA in this tabulation of the data, we see there is no NA. We can see C, S, and V this many times in this table, which has 52,372 rows. So this just indicates this must be a real data set. This is not Iris or empty cars or Titanic. This is a real data because it's just too much. But still, oftentimes this is what we have to deal with, and why this is so large. So we have like 400-ish sites, but at each site you have multiple individuals of the same species and multiple species. So this is how you get such a large number of rows in this table. Now back to the behavior codes. These are songs, calls, or visual detections. So for example, we are only concerned with vocalizations, then we want to drop these visual detections. And when we do the crosstab, So we still want all the samples and species to show up, but we want to subset the table as detect type not equal to V. So if we do that, then we get this Y tot, the total count. So now we have site ID as a row and species ID as column. I'm not going to print it because it's huge. So if we want to know how big it is, we can use this dimension method. 4,500 times 150. So there's also this melt function, which is just a reverse to xtab. If now we want to turn that back into a data frame, then we can do this reverse. And why I'm showing this to you, so our original table didn't have an abundance column as we had with the dummy data frame, but instead those rows counted as individuals because each and every individual was counted and added as a separate row. That's why you don't see anything on the left-hand side in the formula, right? So we only have tilde, site ID plus species ID. This is not always how you get the data. So if you get something like through the reverse, you can see site ID species and then maybe 2 individuals. Then you would be able to see value tilde rows plus calls if you have such a data which includes an abundance column. But right now, we didn't have that abundance column. We were just counting the rows. So this is just an example, kind of turning this back into this aggregate format where you have one row for each site species combination. And you can see from 50,000, this gave us 33,000. So we dropped 2/5 of the rows this way, because those were just multiple individuals of the same species. And also this is where this sparse representation's other advantage comes out. And another reason why I did this reverse, so that we can compare these objects fairly. So you can see the object sizes in, I guess, megabytes. We have this Y total, and then the dense matrix version of that gigantic table, and then also this YREV. So that's the corresponding data frame. And you can see huge differences across those in terms of their sizes. And the last number is the matrix fill. So these are all related to the original data. The sparse matrix is even more efficient than the data frame, the long format, although it has this wide representation. The dense matrix is 7 times larger, so you'll need more memory to keep that in. And that's just because it stores the zeros. And this is just an indication of the matrix fill, which is the proportion of non-zero elements in this table, and that is close to 5%. And this is why I think this sparse representation is really useful, because we don't want to store all those zeros, which make up 95% of the data. Then once we have this big matrix, we do some checking. We have a really suspicious max abundance of 200. This is too round of a number in such a high range. So we can calculate the max, obviously what we are doing, and we turn this Y tot into a regular matrix and use the apply function, which is going to apply the max for each column. This is what this 2 means. And then we sort it so that it goes from lowest to highest. And then if we look at the end where we have the 200, then that's Canada goose. Probably we are not going to run a model for this species, but now we understand it was probably a flock. And you can also look at overall mean counts just using column means, and then you get this long vector with all the species, the mean counts sorted. So you see a bunch of species don't even have detections because those were just, the visuals were detected and not any kind of vocalization. Now what we want to do is to take a species and its count and then join it together with the other data from that survey table. So we're going to pick ovenbird as an example. That's quite often used in all kinds of papers as an example species. Its biology is well understood. And so what I often do is I store the species name as a variable. And this way, if you want Tennessee warbler, then you just replace this line with Tennessee warbler's 4-letter code and run the rest to get the models for a different species. So now we have this species and some info. What is its name? Sirius auricopilus as a scientific name. Quickly checking the sample IDs. That's another function I wrote because nothing like this existed, and I always paranoid that I'm going to just not do the right join or will miss 100,000 observations just by mistake. And what this does, I'm looking at the row names from the survey table and row names from our cross tab. So this is X, this is Y. You can see how many different names you get in one versus the other, how many of those are in intersection, the union of those two, and then the set difference, what you get in X but not in Y, what you get in Y, not in X. And this just gives me an idea about whether this is something I would expect, or if I see intersect is a lot less than any of these and I get a lot of differences, then I might want to look into what is happening there and why am I not getting the right joins, because in the join, you're going to get either the intersect, and then you might miss out on a bunch of species or sites, or you get the union, but that is going to contain a lot of missing values, which is also not very super useful for analysis when you have these holes in the data set. What we can see here is that everything lines up nicely. That's because I've spent some time checking this data. That might not always be the case if you are looking at the data set the first time ever. Now we take the survey data, just call it X, so that it's shorted to type. And then we are going to add the column called Y. And we are just going to take that column called oven, because we stored that in SPP. And we want to make sure that the ordering of those values is going to follow row names of X, which is this survey table. So now we have that Y column, which is our ovenbird counts. And you can create a quick plot of the count distribution. You get this many zeros, ones, twos, threes, and the highest count is 6, which is a bit high, but not unplausible. Now the next question, once we have a nice data set, is we want to fit a species model, and then now we want to understand what is driving the species abundance, why counts are lower in one place and higher in other. So let's have a look at the predictors that we are going to use. We load a couple of libraries, SF for simple features, that's the latest and greatest of spatial libraries in R. It is replacing the old SP package and its associates raster that's still powerful. And we have this raster stack data for the JOSM area with the land cover information. So this is how that stack looks like. It has some extent and projection details, but also these are the layers that you can find in that. So these were also part of the survey table as columns we saw before: open area, water, agriculture, urban, industrial, all kinds of forest stands within 1 square kilometer raster. So this is not super useful for real analysis, but it kind of is going to be useful for us to play with. For real analysis, you probably want to go smaller, like a 250 meter raster or some kind of buffers around the point count locations, which is something we are not going to do now. So if you want to show all your sampling locations on a map, then you can take that X, specify which are the coordinates and what spatial projection it is in. It's lat long EPSG 4269. So now we have this XY simple feature object that we now need to transform so that its coordinate reference system is going to be the same as our raster. So we take XY, which is still kind of a data frame, but with the geometry associated with it. And then we take the CRS, coordinate reference system, from our raster stack RR. And then just a way of visualizing this. I'm just doing it here. Okay. Figure margins too large. What am I doing wrong?
Sometimes I get that error when the actual plot window is too small. Oh.
Yes, that's why I cleared the device, because sometimes you have some margin set that it's not liking. So this is the raster. I'm just showing a water because that gives us an idea about where we are. So this is Peace River, Lesser Slave Lake, Fort Mac is somewhere here. And these are the points. And if this kind of looks similar to what we saw in the slide before, that just means, yeah, we didn't misspecify the coordinate reference. And if we were to extract the information now, it would make sense. Otherwise, we have all these layers that we can work with. And this is already extracted, but if we happen to build a model and we want to make a prediction based on these values, then these are the kind of spatial rasters we would use to make that prediction. Open areas, wet coniferous stands, deciduous forests, kind of their amount in 1 square kilometer pixels. What we also often do is that we have this really fine scale data set, spatial information or some kind of field measurements. And then we think about how to simplify those and how to maybe add up different forest stand types to just simply have a variable which is going to tell us the amount of forest in that piece of landscape. So we can take these deciduous, coniferous, wet coniferous columns, add them up, and create something called forest. Or just take agriculture, urban industrial development, and roads and call it alienating human footprint, because it just impacts the soil, removes the vegetation. So we tend to call these as alienating human footprint. And then you can also add up open wetlands, treat wetlands, and the amount of water in the pixels and call it wet and water. Just to stick with 3-letter acronyms for AHF and wet. Another thing, which again doesn't make sense at what case scale, but is often useful at smaller scales, is to take these amounts. So you can think about this as composition. If you add up all of these values, you get 1 because they sum up to 1. And in a given pixel, this is the amount you get from the different types. And so what we often do is we are interested in what is the dominant feature in that buffer or environment. And so let's just specify the column names here. All these are what we get also in the raster, but now it's going to come from our table X. So we already have these extracted from the rasters. And if you look at the summary of the row sums for these columns, you see it is all 1. So the summary just verifies that, yes, these are adding up to 1. So all of that landscape is summarized. You can also look at the correlation across these and see how they relate to each other. And wet coniferous is negatively correlated with upland deciduous forests and so on. So this is another nice way of looking at how correlated your predictors might be so that you don't end up with having multiple of those highly correlated ones in the same model, just in case those happen to be complementary in one way. So if you want to find the dominant feature based on this compositional data, there's a function called find max. So this takes a matrix or data frame as input. And in this case, we know X with column Cn, all those add up to 1. And I want to find, so if I just look at one row, let's say the first one, I want to be able to look at each row and see where do I find the largest number. It's this one, deciduous 85%. So I'm going to say this CL10102 site, I call it deciduous because 86% is high enough for me. That's a deciduous stand. Now find max is going to find this maximum value and repeat that for all the rows. This histogram just shows you this number, what that maximum value was, and it's pretty much all higher than 0.4, very few that have less. And so the return object, this H, has 2 columns. One, the index, which is the column name, this is here, and then the value corresponding to that column in that row. You see it here. So this table then is going to give us how many times each of those were found to be the dominant one. And if you look at this, soft linear was never dominant, road 2 times, but probably we should exclude those. So once you have a look at these, and agriculture, very few. So probably we should put them together with urban industrial. So once you look at this breakdown, then you start thinking about how to collapse these features even further. But we are not using this right now, so let's just leave it for later. These are the common tasks when we want to deal with these predictors, and a couple of examples and exercises for you while I look at the time. 11:45. Yes, I think we're a bit behind, but not too much. So let's just stop there for a few minutes. So you can use summary or histogram for one column at a time or for the whole table. You can use summary and just kind of look for unexpected values. If the range is not quite right, or you see like negative values where there shouldn't be a negative value, that's a really easy and quick way to troubleshoot things. Histogram, again, you can kind of look at whether you need any kinds of transformation or whether things are really skewed. Table for categorical variables, then often it helps to have a plot of 2 variables at a time, or more than 2, like a scatter plot matrix. Or if you have 1 categorical and 1 continuous variable, what you can do is to use box plot, which is going to give you those box and whiskers for the different categories. And you can kind of just look at the variables and make sure that nothing is out of ordinary. So with this, we're done with the data processing steps. And let's do regression. Now we have everything together that we need. We have X, which is all the columns in our table X, and Y, which is just that one column with the Ovenbird counts. So what we are going to do is to look at how Y column is influenced with other columns in that table.